Yeah, I think we're back at it. How's it going? I think we're in there. I'm Van. I'll be the next speaker. I'll be here for next, I guess, at least 5, probably less than 7 hours, and we're going to be talking about some stuff. We're going to do some more accounting stuff. We'll do some more involved things, and we're going to use a couple techniques that maybe at first we have pigeonhole principle. That's, I guess, here. I can gesture. I guess you can just gesture to the box. That's kind of nice. We have displayed there. And then we'll go into inclusion-exclusion principle, and then we'll have recurrences to finish this off. We get some cool problems. We were lucky enough to draw the long straw, I guess it was, in this, or yeah. Cool, all right. Let's figure out the buttons. Okay. So first problem isn't so bad. I think I solved this one this morning as I was getting ready to come in. So the problem is going to be, suppose a drawer contains red socks and blue socks. How many socks do we need to pick without looking to be sure we get 2 of the same color? So this is maybe a motivating problem. So I claim it's certainly possible. You're going to need to draw at least 2 socks to get 2 socks of any color. If you want 2 socks of the same color, well, it's possible if you draw 2 socks for the first to be red and the second to be blue. So it's definitely possible to draw 2 socks of different colors. But I claim that suppose this happens. I could have also drawn 2 red or 2 blue. I draw a 3rd sock now. So either I got 2 red or 2 blue, my first 2, or I had to have gotten 1 of each. So if I have 1 of each, when I draw this 3rd sock, in the case of it being red, it forms a pair with the first draw. Or in the case of it being blue, it forms a pair with the second draw. And this is like the key insight of what we're going to talk about now, is there's this idea is if I draw 3 of them, at least 2 of them have to be the same color. And this is going to be a flavor of things going forward. And the idea here is no matter what, after drawing 3 socks, 2 must be the same color. Same color. So we're going to take this idea that we have going forward, and this is we're going to build our idea of, as displayed on this previous slide, the pigeonhole principle. It just formalizes this in a little bit more broad detail, which is going to be as follows. So the pigeonhole principle is here. No matter how n+1 pigeons are distributed into n pigeonholes, some pigeonhole will have at least 2 pigeons. So this generalizes this problem here. Instead of it doesn't have to be pigeons, it doesn't have to be pigeonholes, but it is somehow the most charming way to phrase this problem. Here, this statement was, here we had our socks were our pigeons, and our draws were our holes in the idea, or our colors were the holes. And so after you draw 3 socks, you have 2 of the same color. So this is what we have going on. So we're generalizing this idea, and we're going to abstract it in a couple different places. Most of these problems won't deal directly with pigeons and holes, but some of them might. Okay. There we go. So let's do this next problem. How many cards do we need to draw from a standard 52-card deck, keeping in the theme of the last talks, to get 2 cards of the same rank? And next we'll do how many cards we need to draw to get 2 cards of the same suit. Okay, let's first look at 2 cards of the same rank. Okay, this one's for the audience. People have been a while. How many ranks are there? 13. 13, yeah, 13. So we have 13 different ranks. And so at any point, if I draw 2 of the same, I can be done. The first thing I do is I claim that if there's a way for me to draw 13 different cards and get 13 different ranks, I can grab 1 of each. Okay? But I'm going to lay out these 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and I'll label them ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So the idea with this is I'm taking my idea of the pigeonhole principle, and I'm thinking that my holes are the ranks of the cards. And here, the pigeons are going to be cards that I draw. And so the pigeonhole principle tells me, here I have 13 different ranks. It tells me if I draw one more than 13 cards, 2 of them will have to be in the same hole. So the idea is here with 13 ranks, pigeonhole principle, which I'll shorten to be PHP, says that if I draw 14 cards, I draw 14 cards, 2, or really at least 2, must be the same rank. Okay. So this says how many cards we need to draw, and I'm going to define something. This is something we call sharp. So the idea is I know that if I draw 14, I'm guaranteed, and it's possible to draw 13 and have them all be different ranks. So there's somehow an interesting transition from 13 to 14. It's also true if I draw more than 14 cards, that 2 will be of the same rank. If I draw 20, I will have drawn 14, and so 2 have to be the same rank. But this sort of tells me something interesting. The idea is, so at 13, I can draw 1 of each rank, and at 14, I finally begin to guarantee that I have 2 of the same rank. Okay, next let's look at the case of how we look at having 2 cards of the same suit. Okay, same suit. Okay, does anyone know how many suits there are in a standard 52 deck of cards? Okay, how many are there? I suppose it's a better question. Is that a 4? Yes, 4 different suits. 4 different suits. Those are going to be our pigeonholes. Those are going to be we have hearts, spades, in sort of no particular order, diamonds, and clubs. And the first thing I'll notice is it's definitely possible to draw 1 or 4 cards and get 4 different suits. For instance, you can draw all the 3s in the deck, and you would get 1 of each different suit. But using the pigeonhole principle, PHP says that if I draw 5 cards, which here, the cards that I draw are my pigeons, 2 must be in the same box, or at least 2 will be in the same box. At least 2 of them will be the same rank. Okay. Suit. Indeed. Suit. Yeah, that's more true. Okay. All right, so let's talk a little bit about this. I think holistically it's nice to talk about the pigeonhole principle now. So the idea is that it's sort of formalizing this sort of natural idea. This isn't the craziest thing. The sock example is something that maybe everyone feels like they were born knowing, and these aren't the craziest problems either. But it ends up being a very, very powerful idea. We end up being able to think about breaking these problems into these different boxes and then having multiple of them ends up being really, really powerful in discrete math. One thing that maybe is worth mentioning is when we do this and say I draw 5 cards, I'm claiming that 2 of them are the same suit. I'm not really telling you what suit that is or which cards they are. So there's something that the pigeonhole principle guarantees, which is sort of this sort of existence thing, but it's not telling me what that suit is or what those cards are. So we call this it's a non-constructive. It doesn't say, hey, you draw these things and it tells you what those 2 things are. It just says it must happen in this sort of way. So it's sort of powerful in its generality, but you don't exactly get concrete information every single time you use this. But we can still do a bunch of cool stuff with it. Cool. I'm used to asking for questions whenever I go to a race, and so now I can ask for questions. So any questions? Yeah.
I think I get what you're saying, but the whole pigeonhole principle thing. But I mean, is it really saying for the cards example? The first 2 I draw could be the same rank. It's just saying that you're saying how many do I have to have in order for it to be?
Yeah, absolutely. Yeah. So the question is, I don't know how audible this is that it's possible to draw, you don't need to draw 5 cards to guarantee that you have 2 of the same rank. You could draw the ace of hearts and the 2 of hearts. You could draw all 5 of the same suit. That's possible. It would be a flush, and we know how probable that is. Yeah, so this is more a statement of guarantee. So there are arrangements to not do so, and the idea is oftentimes we think about, well, what if there was someone working against you, and they were trying to make it so like as long as possible, you weren't drawing the same suit. You would know in that case, well, as soon as I draw 5, I'm guaranteed to have this. So oftentimes you can think about, well, what if there was someone working against me? How long would I have to do this thing until I had 2 of the same suit? Yeah, but this is, so this is an important distinction I think that you're making. This is different than saying that I have to draw 5 cards to get 2 of the same suit, because certainly you could do it after drawing 2 cards. And the same with the sock example. Sometimes if you reach into your drawer, you draw the first 2 socks out, maybe they're both red. But sometimes they could be red or blue. Yeah, okay. Next, go to the next slide. Do some erasing. So this slide here states, how large of a community guarantees that there will be 2 people with identical letter initials. Sometimes initials can be a nice thing. Maybe you want to have like a monogrammed suitcase that says, who you are, and that sort of, can cleanly identify you. But maybe you go to the airport, and there's a lot of people at the airport. Maybe someone else has the same initials as you. You want to avoid that. At a regional airport here in Missoula, we have a smaller airport, so maybe not enough people go through there every single day to worry about this sort of thing. Let's figure out if we can guarantee that there will be some sort of problem with this though. So first thing I want to think about is I want to use the pigeonhole principle on this problem. So I have 3-letter initials, and for this problem I think that I'm going to say that the order matters. 3-letter initials. Okay, so my name, please don't dox me, is Van Miller Magnin. And so my initials are VMM. I'm going to list just one thing that they're not. Not MV. Right? So the order in which I pick these things is going to matter here. So, and it's not just VM, where so it's 3 letters here, and so it's not this one. It has to be in the order of my names. So assume people have 3 names. This is an assumption we're making. It's a made-up math problem. This is sort of there's 80 watermelons, Okay, so my first question is how many 3-letter initials are there? Okay, and this is something we also see in math and in especially in discrete math. We're building off some of the ideas that we had earlier. So here you can think about the product principle coming up. The idea is I have 3 letters or 3 options, and here I have 26 options for my first letter. I have 26 options for my second letter, and I have 26 options for the third. So this is 26 to the power of 3 total 3-letter initials. Okay? So now the statement is, I claim, first off, it's possible to have this many people who all have different initials. And you can just think about one of them has the initials AAA. The next one has the initials AAB, AAC, AAD. This is sort of a number represented in hexadecimal, I suppose you can think of this as being. This is like, a number in base 26. And so it's that many people. So the idea is you can think about having this many people with different initials. But pigeonhole principle says that if I have 26 to the power of 3 plus 1 people, here my people are my pigeons, and the holes are going to be 3-letter initials. 2 of them, or really at least 2 of them must have the same 3-letter initials. Okay. And again, I'm not saying who these two people are, or if there are more than two people, or sort of what these initials are. This is just a sort of guarantee that two people have to have the same. And this is what pigeonhole principle gives us, sort of at first glance. All right. All right. So next we have a problem. I think that was stated earlier. We had 50,000 people in a stadium with 50,000 seats, and we asked how many ways we could arrange those people in these seats. That's certainly a question that we can answer, or have answered. So here we state the problem is if 49,999 people are in a stadium with 50,000 seats, we know that some seat will be empty, even if we don't know what that seat is. So this, even if we don't know what the seat is, this is sort of talking at this sort of like non-constructive notion or nature of the pigeonhole principle. It's going to give us a guarantee, but it's not going to tell us what that guarantee looks like. So I think this problem is interesting because here, I'm going to think about my pigeons and my pigeonholes. My pigeons, sort of counterintuitively, are going to be my seats in the stadium. And the pigeonholes is going to be my people. And cunningly, this problem has been arranged. We'll notice that 49,999 plus 1 equals 50,000. Okay. So this means that actually we can use the pigeonhole principle on this problem. This means that if I have 50,000 seats and 49,999 people, the pigeonhole principle guarantees, we can say says, or it guarantees that at least one person has been like assigned 2 seats in our process. We're thinking about assigning seats to people. And so when one person is assigned 2 seats, we don't know where they are, but we're going to say they can't sit in both seats at once. You can't do that. That's not how it works. I know there might be some sort of statement if 2 seats are next to each other, you could lay in them like a chaise lounge perhaps, but we're going to disallow that. Maybe there's a handrail in the middle or like an armrest to rest your beverage. So you can't sit in both at the same time. So this says that that person can't sit in both seats at the same time. So at any given time, maybe they can bounce back and forth between them, but they can't exist in 2 places at once. So 1 seat is always open. Cool. This is just a normal exclamation. This is not op n factorial, but hopefully that's clear by context. Cool. Questions on this problem? I think this one's interesting because it sort of flips how you might naturally think of a pigeonhole problem. Normally you think about maybe if you had 10 people and 9 seats, you'd have to have 2 people in the same seat. We sort of flip that on its head, which is cute. Okay. All right, I'm not much of a sprinter, but I'm also not much of a marathon runner. I'm going to practice. I'm going to try to stay hydrated throughout this. And we'll see how that goes. Okay. All right. So next we're going to say this is going to be a more, oh yeah, there we go. So this problem is to show that among 5 points in the integer lattice, there exists a pair whose midpoint is also in the integer lattice. So here we're thinking about points that are going to be in the plane. So the integer lattice lives in the plane. I'm going to draw, I know I'm small right now, but I'll draw a picture. So you can just think about points in the plane, and this is R2 if you're familiar. But this is as most graphs that people have seen through high school. Well, then later on in this talk, we'll see a different type of graph. But this is sort of just like, points in the plane. You have x and y coordinates, and those can be any number. But the integer lattice, it's comprised of special points here in which the coordinates are both integers. So I'm going to show some of these points, although it's many more of them, just a subset. So for instance, we have the point like this is 0, 0, 1, 0, 2, 0, 3, 0. And we, for instance, also have points of the form like 2, 7, -3, -8, and 3, minus 9, for instance. So these are possible points in the integer lattice. Okay. And really it'll form like a full grid, and really it ends up looking like this sort of arrangement right here. This is one of those moments you wish for a graph paper on the whiteboard. Okay, and think about this going off infinitely. And so this is a statement, I don't really know anything about these points that I'm going to have 5 of, but I'm going to guarantee somehow through this problem that 2 of them will have a line between them, and the midpoint will be on the integer lattice. So what does this look like? I'm going to try using some color. If the color doesn't work, let me know. So maybe I have this point right here, that's -2, comma, +4. And maybe I have this point right here, which is 3, comma, 1. And so the midpoint is if I draw a line segment between them, a straight line between them, it'll be whatever the middle of this is, which I'll mark with an X. And so the idea is, in general, how do we calculate the midpoint? If I have 2 points, A, B, and so, all right, given 2 points, A, B, and C, D, this is any points in the plane, and so this will be true of any 2 points in the integer lattice as well. Their midpoint is that the average value of their x coordinates and their y coordinates is the point A plus C over 2, comma, B plus D over 2. And again, this is the average of the 2 x coordinates and the average of the 2 y coordinates. And here with an average, it's just the middle of those 2 things. So it's the middle of the x's and the middle of the y's is what's given by this. Okay. And so what I want to note here is for the integer lattice, we need points to both be integers. So we need an x coordinate and a y coordinate to both be integers. And so if A, B, and C, D are both points in the integer lattice, and I want this thing right here to be in the integer lattice, I need to be able to take this sum, divide it by 2, and still have an integer. And similar with this over here. So does anyone know what kind of integers you can divide by 2 and still get an integer? Yes? Okay, you can also tell me.
Even.
Even, yes. So we will say if we want this to be in the integer lattice, we need A plus C and A and B plus D to be even. Even. Okay. So with this setup, this sort of shows what it means to be the midpoint and what it would mean to be for the midpoint of the segment between two points in the integer lattice to also be in the integer lattice. So let's think about this. So let's go back to our problem now. So we have 5 points. We have 5 points. And then what we're going to do is we're going to distribute them into 4 different pigeonholes. These are going to be our pigeons, and we're going to have 4 different pigeonholes. So split them up. Based on into these 4 even x, even y. So I'm going to split it into 4 groups. Even x, odd y, odd x, even y, and then odd x, odd y. So I'm partitioning these into the parity of these. People have heard the word parity before. But I'm looking at each of my points, and so those integers, the integer coordinates, are either even or odd. And so I'm splitting my 5 points into these 4 different groups. So I'm sorting my pigeons into my pigeonholes. Pigeonhole principle guarantees that 2 points, or I have some box right here, such that those 2 points are, or it has 2 points within it. So PHP guarantees that one of these, we'll call it a group, not a mathematical group. One of these groups contains at least 2 of my points. We'll call them x1, y1, and x2, y2. Okay, so I know I have some pair of points, x1, y1, and x2, y2, that have the same parity of each of these. And let's see what happens. Notice when we add an integer point with an even plus an even in the x coordinates, 2 evens add together to be even. 2 evens add together to be even. So if we're in this grouping right here, you'd have a sum, an x1 plus x2, that would be even, and a y1 plus y2, that would be even. If we have 2 odd numbers and we add them together, you're guaranteed to get an even number out. So if we have 2 odd numbers and we add them together, we're guaranteed to get an even. So what does this mean? You can sort of do a breakdown. I'll spare you the details, but in each of these cases, no matter which box they were in, or no matter which group these were in, x1 plus x2 is even, and y1 plus y2 is even. Okay, so what have we done? We noticed that if I have 2 points where their sum is an even number, or so their coordinate sums are even, then their midpoint will be in the integer lattice. And with my 5 points, I was able to figure out by sorting into these 4 boxes that I have 2 of them that are guaranteed to have the x coordinate sum be even and the y coordinate sum be even. And what does this mean? That the midpoint between the points x1, y1 and x2, y2 must be in the integer lattice. So this guarantees and shows the result. And I'll notice again that this doesn't tell me which of my 5 points satisfy this property. I just know that 2 of them must. You might have to go check that by hand. But as an exercise, if you have a napkin around, you can try putting down 5 points in the integer lattice such that none of their midpoints are on the integer lattice, but you might be here longer than us even. Okay. All right, so any questions as I'm going? Anything I've missed? I don't have the chat open. Okay. We'll keep her moving.
Then the numbers in the lattice are about at the limit of visibility.
Okay, that's pretty small? All right.
Yeah, it's on the small side. The rest is good though.
Okay, well, hopefully limits don't show up too many more times in this talk. All right. Okay. So this next problem we're going to say that show that among 5 points in the unit square, that there are 2 at distance at most 0.71. So we have more 5 points that are arranged in the plane, but they're a special part. So the unit square, I'll show this, and I know I'm small still. This is the point 1. The x value 1, this is the point 1. All right. So the idea here is this is a square, and the idea is side lengths are 1. So this is the unit square. And if we want to, we can blow it up even bigger. We just have a square, and the side lengths are 1, 1, 1, 1, 1. So I'm going to put down 5 points, and I'm going to say that 2 of them must be must be of distance no more than 0.71 away. So my first question is, what's the farthest points can be apart from each other in the unit square? Does anyone know? Root 2, yeah. The idea is if these opposite points on these corners are the farthest apart points, and they're of distance root 2, so the farthest distance in a square with unit side length, distance here, that points can be equals the square root of 2. Okay? And I'll notice the one thing, this is an interesting fact that I'm not going to justify right here. Fact is that the square root of 2 over 2 is less than 0.71. That might become useful at some point. We'll figure out where we go with this, yeah. Okay. So what I'm going to do here is I want to think of this as being sort of a pigeonhole problem. So whenever we do this sort of thing, we need to figure out what are our things, what are our pigeons, and what are our pigeonholes. So what I'm going to do is I'm going to split this into 4 smaller squares, evenly, all of side length 1/2, okay? So now I'm going to split this into 4 smaller squares. I'm going to label them maybe just like A, it doesn't really matter, we'll call them A, B, C, and D. I have these 4 smaller squares. And the observation I'm going to make now is that observe any 2 points, in one of my small squares, I'll finish this, will be of distance no more than this distance right here is root 2 over 2, half the distance between these 2 corners. So any 2 points in one of my smaller squares are of distance no more than root 2 over 2 from each other. Okay. So what's going on here? I have these 4 small regions, and I know that any 2 points in the same region will satisfy the property I need. And so what happens next is that pigeonhole principle, PHP, says that if I lay 5 points in the unit square, at least 2 will be in the same sub-box, smaller square. This is really not a technical definition, but I'll put it in parentheses over here. And so what does that give us? So I put down my 5 points somewhere in the unit square. I know that 2 of them are in the same sub-box. Maybe, I'm just going to say, maybe they're arranged, 2 of them are in box D. I don't know exactly which one it is, but I know they're going to be the same one. The distance between those 2 points has to be less than root 2 over 2, which is less than 0.71. So that guarantees what we need from there. Okay, so those 2 points will satisfy the property I'm looking for. Cool. Questions on this one?
What's the significance of points maybe being on the boundaries?
That is a great question. So the idea is, so the question is, if points are on the boundaries, what you would do in that sort of sense is that you can arbitrarily assign points on the boundary to either of these, and maybe you want to say that this is part of root, maybe this is given to box C, this is given to box B, this is given to box A, and this is given to box D. And so any point on this line, maybe your C is in box A. And so this now, the reason why Corey asked that question is because normally with Pigeonhole you don't want overlapping boxes, and so here these things technically overlap. But if you split them up like nicely, and so what does it mean to be close to but not touching? Well, I said we wouldn't talk about limits, so that's maybe a conversation. Yes, I'm not a man of my word today. Okay, cool. do some erasing. All right. All right. Next problem states, a group of 12 friends play 12 total games of chess. So my question is, how large a group is needed so that each game can feature a unique pair of players? So this maybe is similar to a problem. I don't know if people have been around here for 5-ish hours now, but we saw a problem about sumo wrestlers. We wanted unique pairings between Rikishi and we're looking at something similar here. So what I claim is that we can do is we can think about all the ways to find pairings of players, and we can iterate through those and figure out the transition between having more than 12 possible pairings, and then Pigeonhole will no longer be saying that there has to be a repeat. But I'm going to figure out what that is going to be, maybe speak towards a general problem. And then, so I'm going to state, suppose I have K friends, and I'm going to call them players here. Okay? And I think that this is, and I want K to be such a value that I don't have repeated pairings. And so it's going to satisfy this condition. First thing I want to figure out is, what is K choose 2? This is the number of pairings. Using an earlier theorem, you can express this as a, sort of the following ratio. You can write this as K times K minus 1 over 2. So this is K factorial over K minus 2 factorial times 2 factorial, as we saw proved. You can also think of this as being, count all the ways to pick one player in one of K ways, count all the ways to pick the second player in one of K minus 1 ways. However, we've double counted because we could have picked these people in the opposite order. So we divide by 2 to account for that. This is one way to view this. Okay, so suppose I have K players and so it'll be no repeated pairing in 12 matches. Okay, so what would happen? If K choose 2 was less than 12, like if it was 11, Pigeonhole principle would guarantee that there would have had to be a repeat. So using Pigeonhole principle, what does this tell me? This tells me that K times K minus 1 choose 2 has to be greater than or equal to 12. Okay? So I'm taking this information, right? So if I have 12 players and no repeated pairings, that means I can't have been guaranteed by the Pigeonhole principle to have a repeat. And if I had 11 or fewer pairings and 12 games, then there would have had to have been a repeat. So I must have at least 12 pairings with this value of K that I pick right here. Okay, so I need this to be true. And now I'm just going to do some algebra. So this has to be true. I'm going to figure out what K is, and I'm also going to figure out the smallest K can be where it's a number that makes this true. So this means that K times K minus 1 is greater than or equal to 24, multiplying by 2 on both sides. Now I'm going to move this all over to one side where it looks like I have stuff on one side and 0 on the other. So I expand out K times K minus 1. You get K squared minus K. I subtract 24 from both sides. You get minus 24 is greater than or equal to 0. All right. This right here is maybe you've seen this before. This is a quadratic function, also called a parabola. Quadratic function or parabola. Okay, and it looks like this, if you were to graph it. I think it looks maybe here. It opens up. It's negative for a while. Okay, and so this is the idea here is I'm graphing K is on my x-axis, And on the y-axis, I'm graphing k squared minus k minus 24. Okay. So what does this mean? I want to figure out places, values of k, in which this function has an output that's greater than 0. That means I want to figure out outputs that are above this x-axis. So where are those? Those are going to be outside of my two roots, right? These are my special points. These are the roots of this polynomial. So now if k is less than the small root or bigger than the big root, the output will be above this line. So these are the things I need to care about. So if I figure out what my roots are, I can figure out how big k has to be. And I'll notice now that k is going to be a number of players. It's an integer. It's a whole number, right? So this is discrete math. K is going to have to be a whole number because we have a whole number of players. You can't have 2.5 friends. Well, maybe you can. Maybe they make a TV show called that. The other thing k has to be positive. You can't have a negative number of friends. You can't be at a deficit in that sense. So I'm going to figure out what this value of k is going to be, and I know k might have to be just the next biggest integer is the idea, after I figure out what especially this root is right here. So to do so, I'm going to find the roots of this equation. I'm going to do so by completing the square, just to make my students mad. Okay, so I'm going to complete the square. Complete the square. So I look at this piece right here. I want to think about looking at k minus 1/2 squared. The reason why I'm looking at that, I'm looking at half of this coefficient, this -1. What happens when we expand this out? You get k squared minus the cross terms is going to be minus 1/2 k minus 1/2 k, 1/2 k plus 1/4. All right? You can combine the middle terms. This is k squared minus k plus 1/4. All right? So this looks a lot like this piece right here, and this is what completing the square does. We're trying to take something that looks like this and write this plus or minus a number should be equal to this thing right here. And so they're different they have the same k squared term, they have the same k term, but they're different by this constant term. So what does this mean? This means that k minus 1/2 squared minus the difference between these two right here, so minus, that ends up being, this is 96/4, and this is 1/4, and the difference between those, we have 97/4 should be equal to, or greater than or equal to 0. So in this process, all I have done is taken k squared minus k minus 24 and written it like this. The reason why is because I can now solve for k. I move 97/4 to the other side, and you get k minus 1/2 squared equals, or sorry, is greater than or equal to 97/4. Taking the square root, you have k minus 1/2 is greater than or equal to the square root of 97 over the square root of 4 is just 2. And so here what do we need? We need k equals positive 1/2 plus the square root of 97/2. Now some people, certainly some of my students, would say, you did something wrong here. Does anyone know what I sort of did wrong or hid in this calculation?
Change the greater than or equal to an equal sign?
Oh yeah, sorry, you're right. That is something I did wrong. I didn't even notice I did that wrong. That one I did wrong for sure though. What I did was, I didn't say that this was equal to plus or minus something going on. The idea is I know that k is going on here, and I didn't track this plus or minus through. The reason why is because I knew I needed a positive root. I only needed one of these 2 points, and the plus or minus comes up, but looks at 1/2 plus or minus this value. So the idea is positive 1/2 is halfway between those roots. You either go plus 97/2 or minus 97/2 to get to the other one. But I knew I wanted the positive root, so I hid that under the calculations. So if people are mad at me, I did it on purpose, and I don't regret it. Which is, I guess, my mission. So what is this number? What is this? This is about, I don't know if people know this one off the top of their head. K needs to be greater than or equal to, it's about like 5.24 maybe. It's 5 and a bit. So 5 has to be, or k has to be a positive number bigger than 5.24. So does that mean that means k is bigger than or equal to 6? All right. And so with this, let's look over here. Let's think about what this means for our problems. This is sort of telling us that if I have 6 or more friends, I should have, or 6 or more players, I should be able to arrange it in a way that I don't have repeated pairings. What if we have 5 or fewer? For instance, I'm just going to look at what if I have 5 friends? 5 friends. The number of pairings is 5 choose 2, which is 5 times 4 over 2, which is 10. Okay? So if I had 10 pairings, that means, and I had 12 games, 12 is more than 11, but Pigeonhole principle would say, PHP would say that a pairing was repeated. Pairing was repeated. And as it turns out, 6 choose 2 is 15. And 15 is more than 12. Y'all probably knew that. So the idea there is you can make it, you can arrange it in such a way that the pigeonhole principle doesn't guarantee that a matchup isn't repeated. So this tells us that we need it to be at least 6, and we're seeing again here that with 5 players, pigeonhole principle says you're guaranteed to have a, I keep wanting to say a word, collision, and I can't yet, but maybe one day soon I can say the word collision. All right, cool. Any questions on this one right here? People feel okay about this? This is nice. This is, I'm sure everyone, chess has been on the rise, I think, since 2020, and so this is probably the reason why people like to complete the square. And
It seems that it wasn't necessary to complete the square, if I may offer.
well, what would you have done instead?
Plugged in 5 and then it wasn't big enough and then plugged in 6.
Oh yeah, certainly we could have brute forced this. That is true.
But otherwise, yes,
You
I
could
agree,
you could
it's a
have
different number.
numerically approximated. So the idea is people think about the quadratic formula. Quadratic formula is just doing the completing the square process, but skipping to the punchline. I will admit the first time I did this, I plugged it into Wolfram and asked for the roots, and so they were these things. But I wanted to do this here. This is how you do it. So maybe this is a refresher. That's some of the fun of math is that you're always reaching back to things you've learned in the past. And then forgetting other things while you reach back for them. If you ever reach for something as you fall and you drop what's in your hand, that's math. So it's nice to learn to complete the square again. Okay. So now I'll present, is it?
Oh, sorry.
Cool. All right, so now I'm going to present this as the generalized pigeonhole principle, which takes these ideas of the pigeonhole principle we've been talking about and extends them further. I'll justify it a little bit, but I'm not going to go so far as to maybe prove this, but this would hopefully make sense. Okay, this says that no matter how n pigeons are distributed into k pigeonholes, some pigeonhole will have at least n over k pigeons, is the idea. So before we looked at just sort of some numbers, we had an n plus 1 and something had at least 2, but you'll notice that n plus 1 over n is a little bit bigger than 1, so to be at least a little bit bigger than 1, you have to be 2 for whole numbers. So this is sort of, this extends the ideas we had before, but you can think about this, the idea is, so suppose you have maybe you have 12 pigeons and you have 4 pigeonholes, one of them has to have at least 3. The idea with this is okay, well, suppose none of them have 3 in them, you add up 2 a bunch of times or 2 4 times, and you get 8. And so you don't have enough pigeons. And so if you have less than this amount in each of them, you sum them up and you don't get enough. So this extends this idea that isn't too crazy, but it is quite useful. Okay. So let's look at this. We're going to use the generalized pigeonhole principle to argue that there must be a set of 2 to the 384 different inputs to the MD5 algorithm that give the same, sorry, this last word should be output. That's on me. There's going to be a few of those as time goes on. It's going to go more and more off the rails. We're still Okay, we're about 15% of the way in. 15, maybe 17, yeah, we'll see how this goes. Okay, so what is going on with the MD5 algorithm? It is a hash function algorithm. It takes as input a string of data, and then it maps it to another string. And the idea is, the reason why you would do this is that maybe you have limited memory, so we're taking something long that uses a lot of, like a longer string, and we're mapping it to a shorter string. So the MD5 algorithm, I don't know why there's the word which in there, takes as input a 512-bit string, and it outputs a 128-bit string. Okay. Make this small again. And then make me big. Okay, I'm huge. All right, so my first question is, how many 512-bit strings are there? This is some computer science speak. Are there? So first we'll translate this. What we actually mean is how many binary strings of length 512 are there? Binary strings of length 512 are there. Okay? Well, let's think. You have 512 places. You could put a 0 or a 1 in the first spot, a 0 or a 1 in the second, etc. There ends up being 2 to the power of 512 different strings. Different strings. And using back to our idea of the generalized pigeonhole principle, this is going to be, I'm going to call this n. This is our pigeons in this problem. The next question is, we're taking these long strings and we're mapping them to shorter strings. And so the idea is that's what's going on there, is we're taking our pigeons and we're putting them in pigeonholes. So the question number 2 is going to be, how many binary strings of length 128 are there? It ends up being here. We'll have, I'll call this k, and this is going to be 2 to the 128 different strings. All right. So here we have our pigeons and our pigeonholes, and the pigeonhole principle says that if I put n pigeons in k holes, there must be one of these pigeonholes with at least n over k pigeons in it. So generalized PHP, which I guess we'll call GPHP, says that some hole contains n over k pigeons. And here, holes are strings that we map to, and pigeons are strings that we start off with. So what does this mean? This means that in terms of our algorithm, this means that there exists 128-bit string that or that at least n, which is 2 to the 512, over k, which is 2 to the 128. Anyone know what this is off the top of their head? Off the board, maybe? This is going to be 2 to the 384, conveniently. 2 to the 384 512-bit strings map to. Okay. So what's going on with this? I guess we can do a quick aside. I'm no computer scientist, but this is something of interest to computer science, and so this is how the pigeonhole principle comes up in other places. The idea is that this is called a collision, having two long strings mapped to the same shorter string. And in computer science, this is not good because it's confusing. You're no longer able to recover all of your information. So it is of importance to figure out, hey, if we have strings that come up a lot, we want them to map to values that aren't mapped to by other things a lot. So you want to maybe rank your common 512-bit strings and say, okay, my really popular ones get their own, 128-bit string, and things that don't come up very often maybe aren't mapped to like this. So you might use the pigeonhole principle out in the wild like this. All right. Okay. This is a problem that I think is quite nice, and so I'm going to talk about it. I'm going to smile while I do. So here this says every point in the plane, or in a plane, is either red, green, or blue. They've been colored by someone, maybe an antagonist. I didn't get to choose. Does there exist a rectangle in the plane such that all its vertices are the same color? And the answer, first, I think your answer might be maybe, and then you're like, well, it's a coin flip, yes or no. So you got a 50-50 shot. But with the pigeonhole principle, and even the generalized pigeonhole principle, we can have a definitive yes. Okay. So the answer is yes, and I'll say why. I'll explain why. That's sort of the name of the game. Okay. So suppose the board right here is my plane. This is, the two-dimensional plane, and think about all the points in here being colored red, green, or blue. I'm just going to look at the 4 by 19 integer lattice given by points that look like this. So it's going to be, maybe I have, this is my plane, these are my coordinates, and here I have the points 1, 2, 3, and 4. 1, 2, 3, 4. And then I have 1, 2, 3, and then I'll do a dot, dot, dot to be suggestive. 18 and 19. This is 1, this is 2, this is 3. And so these are just marking this off. And the points I care about are not going to be on these axes. They're going to be the points that are sort of bounded in this rectangle here. So this will be 1, 1, 2, 1, 3, 1, 4, 1, 1, 2, 2, 2, 3, 2, 4, 2, 1, 3, 2, 3, 3, 3, 4, 3. Things are happening in the middle here. I didn't want to put 19 rows, but maybe if we have time later, we can do that. And then up here we have 1, 18, 2, 18, 3, 18. Oops, we'll make these a little better spaced. 4, 18. Finally, 1, 19, 2, 19, 3, 19, 4, 19. So the first thing I want to notice is that, maybe I'll highlight the box I care about.
And to be clear, every infinitely many points are covered.
Oh yeah, every infinitely many points are covered. I'm just looking at 76 of them. Some 76 in this special arrangement. The reason why I looked at things in a special arrangement is because these are rectangular in their arrangement, so I'm going to look for a rectangle that lives in here. So there might actually be a lot of rectangles in this box. But certainly, all of the infinitely many points are colored. So I'm looking specifically in here. Okay. Let that pen sing. All right, so let's notice what's going on. I want to look at first this top row right here. I'm going to say, look, I have 4 different points, and all the points have been colored by 3 colors, red, green, or blue, right? So what does the pigeonhole principle tell me about points on this top row? I have 4 points, and I have 3 colors. PHP says 2 points in this row have the same color. Right? That feels right. So we don't know what that color is, but maybe two of them are green. And so let's call this row green. Just say the whole row is, call it green. Maybe call it G. Call it whatever there's at least two of. And if there's two of one color and two of another, break the tie arbitrarily. I don't mind. The idea is I'm going to label this row red, green, or blue. And I'm going to do that for each of my rows. Do this for each row. Okay? So I have 19 rows, and they each get a label of red, green, or blue. Okay, so I have 3 different labels that I could have given a row to, and I'm going to think about those being holes, and I'm going to think about each row being pigeons. And so what happens is that we says that generalized pigeonhole principle says that some, or really what it'll say, so it says that 19, or at least 19 over 3 rows are the same color, are given the same color label, the same color label, right? So this is just a generalized pigeonhole principle. I have 19 things, and I label them all in one of 3 ways. So one of them has to be given at least 19 over 3 of the same thing. And what is this? What is 19 over 3? It's a bit more than 6. So what does this mean? Like notably, so at least 7 all have the same label. Okay? All right. So that means that I have 7 rows, or at least 7 rows, that all have at least 2 of them with the same color. So okay, so now I've like honed this down. I'm looking for possible corners of my rectangle, and I have these 7 different rows where at least 2 of them are the same. And so the idea is, if I could find, for instance, maybe I have this row down here is labeled red, and these 2 are both red, and I have some row later on where the same arrangement inside the row, I have 2 arranged in the same way that are also red, I can form a red rectangle like this. But that can only happen is if I have 2 of the same arrangements. And so the question is, how many ways can I choose 2 of these to be red? And so I had to pick 2 of them to be red to get this sort of label. So the question is, how many ways can I do so? How many ways? Many ways to have 2, I guess, or more red in a single row. Single row. What would I do here? I have to think about, I have 4 spots, and I'm choosing 2 of them to be red. So that's 4 choose 2. 4 choose 2 ends up being 6. Okay, so I have 6 possible ways to have 2 of these be red. But I have 7 columns with the same label, so I have 7 different rows that have 2 reds. So 7 rows, and only 6 different ways for them to be arranged differently. So what does that mean? That means that by PHP, we're moving all over the board, 2 rows of the same color have 2 points of same color. We're really at the bottom of the board now. I'm going to go kind of squirrely. 2 points of the same color in the same arrangement. Same arrangement. So what does this mean? I have 4 choose ways to arrange 2 points within here, and I say that I've done so the same way in 2 different rows, and so those 2 will make my red rectangle. Maybe these 2 right here, and those 2 right there, here. those 4 will make this rectangle. So what's going on? We've used the pigeonhole principle a lot in this problem. We figured out that that every single row across had some color show up at least twice. Okay, and so we gave a label to each of those. This means that, and then we looked at using the generalized pigeonhole principle, we saw even more than that, there was 7 different rows, all with the same 2 colors showing up at least twice. And then we looked at, okay, all the ways we could arrange 2 points. This meant that we had at least 2 rows, using the pigeonhole principle again, such that we had 2 points in the same arrangement of the same color. So they had to be, for instance, red, red, and red, red. And those 4 points, because they're arranged in this sort of rectangle, form a rectangle. So this is the proof here. Cool. All right. Questions on this? Anyone feel okay? Like this? Nice? Yeah. One thing I will note, just touching back on a question that came up earlier, the idea is you could have, maybe had you artfully selected the 4 points at random and maybe you only needed to look at 4 points to get a rectangle, but maybe if someone was working against you, it would be hard to do this. So yeah, this is nice. This is, again, this is cool because we're looking at this sort of continuous problem. We're labeling all the points in the plane, but we're able to look at like a discrete subset and use our tools on it. All right, do some more erasing. Okay. So this will be your capstone for this problem, or for this section. So this is a problem, this is due to Erdős and Szekeres. Maybe it's a specialization of their result. I think this was proved in 1935, according to Wikipedia when I looked this up on Saturday. Maybe it's changed since then. So what we're going to show is the following. Show that every ordering of the first n squared plus 1 positive integers includes an increasing subsequence of length n plus 1 or a decreasing subsequence of length n plus 1. So for a subsequence to be increasing, we want every integer to be bigger than the last, and for every a decreasing subsequence, we need every number to be smaller than the last. So for instance, maybe if you have the numbers 1, 2, 3, 4, 5, I'll show you an increasing subsequence of length 3. Inc. 1, 3, 4. Every number is greater than the last. And maybe we'll do a decreasing subsequence, which is 5, 2, 1. Every number is less than the last. And then it's also possible to have a neither. So this is neither increasing nor decreasing. Maybe you have 1, 4, 2. So it goes up for a little while, then it decreases. So the statement says that, hey, no matter how you arrange these numbers, and so you want to have them like look random, I can find some sort of like interesting structure and pattern of a pretty long length within this. So this is sort of this statement. The pigeonhole principle ends up like answering a lot of these problems, sort of like the last one. There's sort of like a chaotic arrangement. There's a lot going on, and we find some sort of ordered substructure within them, as long as our set gets big enough. Okay. So I'm going to lay down, first I'm going to tabulate something, and then I'll talk about what's going on in my table. So maybe, actually we'll do the other way. So given a sequence of length n squared plus 1, label each number k sub I, and I'll explain what all this means, k sub I, with a pair a sub I comma b sub I. And then so a sub I is going to be the longest, or the length of the longest increasing subsequence, ending at position I, and then B sub I is going to be the length of the longest decreasing subsequence. Ending at position I. Okay, so what does this mean? I'm going to do a table. I'll do one such arrangement of n plus 1 letters for n equals 3, and I'll show what each of the values a sub I and b sub I would be. So maybe we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are my positions. These are my I values. Okay? And so the idea is what comes after I will be k sub I. And so the idea is I've rearranged the numbers 1 through 10. This is a permutation, if you remember those from a while ago. I've rearranged them in some order, and so I'm just going to give that order down below. So the idea is the first position will be 3, and the second position will be the number 2. The third position will be the number 1. The fourth position will be the number 6. The fifth position will be the number 5. The fourth position, this 5 is 5 and 5. In the sixth position, we have number 4. The seventh position, we have number 9. Eighth position, we have the number 8. Ninth position, we have the number 7. In the 10th position, we have the number 10. So these are just my indices in the top column, and this is my actual sequence I'm looking at in the in the top row, and I'm looking at the sequence in the second row. Okay. Next, I'll have A sub I and B sub I, and I'll maybe do these simultaneously. First thing to note is that a sequence of length 1 is both increasing and decreasing. So what's the longest increasing sequence starting with ending right here, in this right here? So going from left to right, we start with 3, and that's the only number we have so far. So we have an increasing subsequence of length 1. We have a decreasing subsequence of length 1 as well, which is just the number 3. Okay, so these are both 1. Next, we can look at this. We want to say, okay, now I'm looking at this part right here, 3 and then 2. And so I want to make the longest increasing subsequence I can, ending at this point right here. Well, 3 is more than 2, so these sort of decreases. So we still only have a 1 in this position. You can only have a decreasing subsequence of length 1 ending here. But we can go 3, then 2, so we have a subsequence of length 2 ending at this position 2. So this will be a 2. Okay, next, if we want to figure out an increasing subsequence ending at 1, well, we have 3, then 2, then 1. The longest one is of length 1. This is sort of not interesting. But if we want a decreasing subsequence, you can go 3, then 2, then 1, which is, okay, 3, 2, 1, so it'll be 3 numbers long. All right, and we'll continue on like this. What about here? So now we have the number 6 in the 4th position. We want to figure out the longest increasing subsequence ending here. Well, we can go 3, 6, we could go 2, 6, we could go 1, 6. Those are all subsequences of length 2. So the longest is of length 2 ending here. And 3, 2, and 1 are all less than 6, so we can't decrease and get down to 6. So the longest subsequence ending with a 6 is 1. All right. And as we go through this, I'll just fill out these values right here. This is sort of, can be like involved, but again, all I'm going to do is look at this and look at the longest increasing sequence of numbers ending with either 5 or then 4 or then 9 as we go through with this. So the longest ending in 5 is of length 2. That's like a 3, 5, for instance. Longest ending in a 4 is also of length 2. That's maybe a 2, 4. Longest ending in a 9, you can go maybe 1, 4, 9. Sorry, you go 3, 6, 9. So you can do something of length 3. Longest ending in 8, you could also do 3, 6, 8. The 7 is also 3. Here, the longest decreasing subsequence ending in 5th position, which is the number 5, is 6, 5. So that'll be of length 2. You can go 6, 5, 4 for a 3 here. 9 is the biggest number we've seen so far. So the longest decreasing subsequence ending with a 9 is just the number 9. That's the sequence 9. Then we can have a sequence 9, then 8. So this will be a 2. This will be a 3. Then here, I'll do the last row last. We can have the sequence 1, 4, 7, 10 is the longest, sorry, 3, yeah, in the first, 4th, 7th, and 10th positions, you can have the numbers 3, 6, 9, and 10. So the longest is length 4. And 10 is the biggest number we've seen so far, so this will be a 1. Okay, this is sort of a lot. This table has a lot going on with it, but I want to ask if anyone notices a pattern in my AIs and my BIs. Yeah, so here we have like a 1, 1, 1, and then a 2, 2, 2, and then a 3, 3, 3, and then a 4. And here we have a 1, 2, 3, a 1, 2, 3, a 1, 2, 3, and then a 1. So there's some sort of pattern going on. As it turns out, these are very specially arranged numbers that we'll look at in just a bit. So we'll notice like what's going on here. We have the number n equals 3. And so here, looking at this value right here, the fact that this is, so because we have n squared is 9 plus 1 is 10. So we have this 4 right here. That means that there is an increasing subsequence of length 4, which is of length n plus 1. So this here sort of is a non-counter example. And the increasing subsequence might be 3, 6, 9, 10. So this is a non-counter example. But you'll notice that if you just had the numbers, the numbers 1 up to 9, you would have arranged this in this way. You would have had 3 squared numbers in some arrangement where you only have a subsequence of length 3. So going from 3 squared to 3 squared plus 1 might do something for us here involving the pigeonhole principle. Okay. So I want to go back to this idea of my sequence. Like I've arranged my numbers, and I have each number is associated with this pair, AI, comma, BI. So AI and BI tell me the length of a longest increasing subsequence at a certain position. All right. The other thing I want to notice is that these AI and BI pairs can never be the same for 2 numbers in the sequence. You'll notice here, they're always different. These are all different pairs of numbers, right? You never have a 1, 1 repeated again. 1, 2 is never repeated. 1, 3 is never repeated. 2, 1 is never repeated as you go through. That's going to be important. Let's see why. Okay. So observation will be 2 numbers must be labeled with a different pair. So 2 of my KIs have to have different AI-BI pairs. They can agree in one of the 2 positions, but they have to be different in 2 positions. The idea is if KI is less than Kj for I less than j, then AI is less than AJ. Let's unpack what this means. So I'm looking at a sequence of numbers. So maybe I have some sequence that ends here, some increasing sequence that ends at this number 6. So maybe it's like, for instance, 3, 6. If I find a bigger number down the way, I can add that to my increasing sequence. I can go 3, 6, 9, or I can go 3, 6, 8, for instance. So for any of these values that are bigger than 6, they have to have a bigger entry in the a sub I spot than 6 does, right? Or in a sub 4. So the idea is here, you'll notice that for every number that's bigger than 6 down the line, it has a number that's bigger than 2 here, because you have an increasing sequence, and you can just tack that number on at the end there. Okay. On the other hand, we can say that if k sub I is, well, this should have been, yeah, so k sub I, this is greater than k sub j, and this is, so if k sub I is greater than k sub j, for I less than j, then b sub I is less than b sub j. And this is sort of getting at decreasing sequences. Suppose I have some number, maybe that's, I'm going to look at 6 right here. or maybe I'll look at this number 5. And so this has a decreasing subsequence of length 2, 6 comma 5. Any number smaller than 5 in this, in the rest of my sequence must have a b sub I that's bigger. And we notice specifically the number 4 has a value 3 here. That's because you can take the sequence 6, 5, 6, 5, which is of length 2, and you can add the smaller value to that subsequent sequence, so you can get something that's 1 longer. And so we notice that, so two numbers must be labeled with a different pair in general. Okay, otherwise you could either increase one of these or decrease one of these, like all of these relationships. One of the two has to be bigger. Okay. Okay, so what does this mean? So like observe, if a sub I is less than or equal to n, and b sub I is less than or equal to n for all values of I, then there are no more than n times n possible pairs of AIs and BIs. What does this mean? So here, these are counting how long an increasing or decreasing sequence is. And so if I'm looking at this problem and I want to say, well, what if there's nothing of length n plus 1? That means that any increasing or decreasing sequence has to be of length no longer than n. And so of these pairs, you have n numbers to choose, 1, 2, 3 up to n here, 1, 2, 3 up to n here. Using the product principle, you have n times n, and this is equal to n squared possible pairs, like this. All right? So if you have n squared possible pairs, you'd have a contradiction arise where if we said, suppose that we had n squared plus 1 points and no increasing subsequence of length n plus 1. That means that we'd only have n squared possible pairs AIs and BIs. So pigeonhole principle would imply that there was some pair that was chosen that was shared by 2 different points ki, but they can't have the same pairs, which is a contradiction, which we haven't really discussed what a contradictive proof is in this setting, but it is a thing. But contradiction is the punchline, as we all know. So this sort of shows Erdos-Sekhares. I will explicitly, I sort of showed it in this tabulation, but we can explicitly see that it's possible to have only n squared numbers and have no increasing or decreasing subsequence of length n plus 1. So I have the numbers. So if I'm given the numbers 1, 2, 3, all the way up to n squared, I'm going to arrange the numbers as follows. I'm going to have them go n minus 1, n minus 2, 2 down to 1. So I'm going to take these first n integers in like reverse order. So this is a decreasing subsequence of length n, but of no longer than, it's not n plus 1, so it's of no longer than that. So I have a decreasing subsequence of length n, but all my increasing subsequences are length max 1 because this piece right here decreases. Okay, so it handles the first n of them. Then I'm going to go at decreasing another piece that's going to go 2n minus 1, all the way down to n plus 2, comma n plus 1. So I take the next chunk of n numbers and I arrange them in decreasing order as well right here. So now notice that all of the numbers in this sequence, this part of my sequence, are smaller than all of the numbers over here. So I can't make a decreasing subsequence of length longer than n. And notice that I can make a slightly longer increasing subsequence. I can take one number from this first chunk and one number from that second chunk and have an increasing subsequence of length 2. Okay, then what I'm going to do, I'm going to arrange 3n, comma 3n. After this, I come back down here. I don't have enough board space to do more. So 3n minus 1, 3n minus 2, all the way down to 2n plus 2, comma 2n plus 1. The next n numbers in my sequence, or in my ordered sequence. And so notice again, this is a decreasing subsequence of length n, but if I want an increasing subsequence, it has to go 1 from these first n, 1 from the second n, 1 from this third set of n. All right, so I have increasing subsequence of length 3, but no decreasing subsequence of length longer than n. And I'm going to keep doing that. I'll do a schematic of what it sort of looks like as we go through. Finally, we'll do n squared minus 1, n squared minus 2, all the way to n squared minus n plus 2, comma n squared minus n plus 1. Pictorially, you can think about these numbers looking like this. So we have the first n form this decreasing subsequence of length n. Then we go above that value, or above those values, so there's a decreasing subsequence of length n. We have another set of n. Then we have everything just above that. We have another set that decreases of length n, and another set that decreases of length n. And so we end up with here, there are n points in each of these little sections, and we have n many of these line segments, these sort of like dust that increases. So if I wanted to make a decreasing subsequence, I could take all of these n points, but I get something of length n, but I couldn't get anything later on because everything is all of the points before this point are smaller than everything after. And if I want to make an increasing sequence, well, I can only take 1 from each of my little sections. Everything after in the section is smaller, so I can't take 2 in the same section. So if I want to make an increasing sequence, I can only take at most 1 from each of these n small lines. So increasing sequences can be of length n, but they're of no more than length n. The idea is if you want to see that, suppose you had an increasing sequence of length n plus 1. Well, pigeonhole principle would guarantee that you had 2 in the same section, so it wouldn't be increasing. So here we see pigeonhole principle again showing up to show that we can't have something of length n plus 1 right here. All right, questions on this one, on air secretors? No? No? 2 thumbs up? Okay, that's good. Well, I'm going to take a sip. Thank you, yeah. Everyone at home, all you listeners, take a sip of water. We're just getting started.
Cheers.
Yeah, cheers to you too. Okay.